department. Today we have Dr. Tim Collett from the USGS. He is the chief. He leads the studies on gas hydrants in the USGS, and today he's going to talk about petroleum systems and how gas hydrants can be studied as petroleum systems in marine and Arctic permafrost environments. So thank you, Tim.
And he forgot this part. Colorado School of Mines.
He's also, yeah.
I'm
He's
an
also,
adjunct professor. You know what that means? Not much.
so you're alum, right?
Excuse me?
You're an alum from mines?
Yes.
And an adjunct professor.
And everyone always cringes when they say that. They actually let him graduate to get rid of it. It did take 10 years. I'm telling you the truth now. So, Tim Collett with the U.S. Geological Survey, what I've had the honor of being with for 35 years. What's old, I should know more. So as I prepared for the talk today, in thinking about it this morning, I had a very nice presentation all set up, and I decided I didn't like it. So I was basically describing everything we knew and things like this. So what I thought today would be a good presentation is try to work through more of a seminar series on some of the things we don't know, some of our biggest concerns. So what we're going to do is start off with a discussion, mainly looking at petroleum systems. But I'm going to look at petroleum systems in one way. I'm only looking at sand reservoirs. And we're going to then look at the engineering aspect of sand reservoirs, how they lead to gas hydrate production. Understanding the geologic controls on gas hydrate production, understanding the engineering controls. So very quickly, the last half to two-thirds of the presentation, I want to focus on mainly reservoir properties. So much like advertised by the title, I want to talk about petroleum systems. Petroleum systems, much like the concept we use for gas hydrates or for conventional resources, is understanding the geologic controls on the occurrence of gas hydrates. So it's a very simple concept when you think about it. We use it for conventional oil and gas all the time. The second half, what was the main thing I was alluding to, is on gas hydrate production. We want to look at two different accumulations, particularly on the North Slope of Alaska, kind of look at some of the things we've learned about gas hydrate production from Alaska, and then look at a little bit at the Nankai Trough. But most of it, we're going to look at some reservoir property data from the North Slope of Alaska, particularly issues of effective permeability, its relationships to hydrate saturation and production, and what we know and don't know, and what different data sets are indicating it, because right now there's a contradiction in some of the data sets. So we're going to start off with a little bit more about what our factual information, talk a little bit more about the geology and understanding the systems, using an example mainly from the Gulf of Mexico, and then look at Nankai, Alaska North Slope. So first off, it's good with any group. This group is a group of experts, so I'm going to do this quickly. When we look at gas hydrates, we always describe the purpose. The reasons to study gas hydrates is like a three-legged stool. You look at the energy resource potential, the operational geohazards, and global environmental issues. Of course, when we look at these, we're familiar with gas hydrates, have a large storage capacity. They store a large volume of gas per unit volume of material. Looking at basically the ability to explore for gas hydrates. We have many well-developed techniques to both explore and to characterize hydrate resources now, but also a fundamental issue is understanding the environmental impact on issues like production. So many of the issues we talk about hydrates are always in two areas, understanding the geology and then understanding the producibility of hydrates. So that's really, well, how much of a resource is there and how much can you actually produce? As an operational geohazard, this is everything from drilling through gas hydrates for deeper conventional resources, drilling hydrates themselves, but also one of the most significant problems that are studied daily virtually with gas hydrates is producing hot oil and gas, conventional resources from depth through overlying gas hydrate accumulations, particularly in marine and also permafrost environments. So as a hazard, both drilling issues, but also producing through them. And finally, as a global environmental issue, one of the ones that most people look at and consider with this is the issue of the atmospheric chemistry, and particularly the global carbon cycle and the role of methane. A number of scientists proposed years ago, about 10 or 15 years ago, was the original consideration at the buildup of the methane in the Earth's atmosphere, what's increasing at a much more rapid rate than CO2, for example, could potentially be to stabilize gas hydrates. That's naturally to stabilize systems and others. So again, we won't really look much at this issue. We're going to focus almost all of our time on the energy resource component. But when we talk about the petroleum system and geologic controls, all these different considerations or motivations are linked. And the linkage is, where do hydrates occur and what are their geologic controls? If I'm studying hydrates to try to understand a resource or try to understand a hazard, a fundamental aspect is, where do they occur? How much are there in that type of setting? And then finally, in a global environmental issue, are they stable in that environment and others? So again, when we look at different components of this kind of triad of looking at hydrates, you contribute to our understanding of hydrates along multiple pathways. When we look at gas hydrates, everyone gets quickly fascinated by volumetrics. How much gas is there within hydrates, both at a global scale, but all the way down the accumulation scale? In virtually every hydrate talk, you kind of have to talk about this issue just to put it into context. This is going to be my only discussion about volumetrics. And basically, it's very common in resources, everything from mineral resources to oil and gas resources, use the concept of a pyramid. A pyramid is used to represent the volume of the resource, but it's also to indicate the complexity and availability of that resource and its different characteristics. So at the top of this kind of conventional, unconventional resource pyramid, we have the conventional resources now being produced, for over 150 years almost, moving into unconventional resources again, and then finally what we know of the unconventionals, particularly shale gas in this era today. The pyramid volume basically indicates the volume of that resource, but also from the top down, it's generally perceived the resources at the top of the pyramid are more easily produced. So the pyramid is inclined to show you basically the more accessible, more easily produced resources at the top of the pyramid, the more difficult to access resources lower in the pyramid itself. So we've added hydrates into this part of the pyramid, showing potentially production out around 2030, of volumetric analysis of how much we believe there is gas within gas hydrates. You often hear estimates of the amount of carbon within gas hydrates is equal to all the volume of carbon within all the known or expected to be existing oil, gas, and coal in the world. So these are these big grandiose statements. But the problem with this, there's no analysis of this volumetric, its characteristics. This is all the way to a molecular count. To disseminated gas hydrates, 1 or 2% by volume in a marine sediment, all the way up to reservoir systems. So we have our own pyramid, gas hydrate researchers do. So we'll come back to this pyramid, but basically what we're saying is not all gas hydrates are created equal, just like not all oil and gas resources are created equal. At the top of the gas hydrate pyramid are basically gas hydrate in sand reservoirs, in permafrost environments, and then in marine environments. The bottom of the pyramid, however, goes through a transitional zone of fracture-dominated systems and others. But most of the pyramid, when we talk about these very large numbers, we hear about hydrates, are likely hydrates disseminated in marine silts and clays. These are not reservoir conditions. So again, when we talk about hydrates, if someone asks you about the resource potential of hydrates and others, it's very critical to understand what hydrates are we talking about. Also within this pyramid are hydrates such as those in fracture-dominated hydrates. These are ones like at the seafloor or in fracture systems and others, and fine-grained sediments. So again, I want to be very important to highlight that we're going to focus most of our presentation on the very top of the pyramid. The lower part of the pyramid, what makes up a very large portion of this volume also, are hydrates very unlikely ever to be produced. What is our toolbox? Where does our understanding of gas hydrates come from? This is a map of all the significant deep drilling projects where I've drilled and studied gas hydrates. We start off with the Ocean Drilling Program, ODP, and the Integrated Ocean Drilling Program back in 1995 through 2006, where we see basically science programs. These are proposed by scientists to study hydrates. They're mainly designed to look at processes. This is our foundation, our first projects to understand the occurrence of gas hydrates in nature. As we move forward, we'll stay focused on North America. We've seen hydrates in the permafrost environment, of course, both within the permafrost and below the base of permafrost. I'm assuming everybody in the room is experts because you're good Colorado School of Mines students, so I'm not talking a lot about background here. We're just going to keep going. Is that we've had major projects by BP, ConocoPhillips, but have all been leveraged with the Department of Energy. So that's a critical aspect. We still see a significant part of government funding in all of the different independent or industrial efforts. These have all focused on production testing and characterization of the resource, and we'll return to both the BP project and the Conoco project for most of the talk today. We also see assessment activities and other analysis. We also see in the northern Canada, the Malik project, you'll see a number of partnerships, including the USGS and JOGMEC. And this becomes a real critical component to recognize. The Japanese National Oil Company, what became JOGMEC in 2006, basically is one of the catalysts for gas hydrates since the year 2005. We see a very large gas hydrate project also in the Nankai Trough, offshore Japan, where we're looking at the resource potential of hydrates in the marine environment. But they've partnered in a number of projects across the world, including northern Alaska and Mackenzie Delta to gain insight to resource potential of hydrates, doing partnerships and projects together and others. Returning to the U.S., we also have projects in the Gulf of Mexico. We had a joint industry project for 8 years led by Chevron that was looking at the geologic occurrence of hydrates in the Gulf of Mexico. That project ended after Macondo with a reevaluation of risk portfolios. And we've returned with a project which leveraged DOE, University of Texas, where we're drilling a 3-week-long drilling program starting in May of this year for coring gas hydrates in the Gulf of Mexico. So again, we maintain an active program primarily on the North Slope and also in the Gulf of Mexico. Worldwide, I've already indicated, we've had a number of partnerships working with our colleagues in JOGMEC, including Malik on the North Slope of Alaska and Mackenzie Delta. But also we've had partnerships where we've worked with core data from the Nankai itself in our laboratories. So it's been a very close relationship. The other major projects we see, of course, is a large project in China. I believe you had some lectures last week, but you had an opportunity to learn more about the gas hydrate projects on the north slope of the South China Sea. We also see projects here. This is a Gulf of Japan, or the EC project, where led by Japan on massive gas hydrate occurrences, not in sand reservoirs, but in outcropping hydrates along the seafloor in the Japan Sea. I just want to finish off the discussion of the Yulong Basin. This is a basin along the eastern margin of Korea, 2 large hydrate drilling programs, again, featuring geologic evaluation of hydrates. And one of the projects we're most closely associated with is India, where we've had 2 large drilling programs for gas hydrate resources, mainly looking at the geologic occurrence, evolving into a future production test that we see shortly. And I just wanted to highlight the Gemusin project here in Malaysia is one of the rare projects in the public domain that deal with drilling hazards associated with hydrates in producing hazards, producing gas through a hydrate accumulation. This was a deep multi-billion barrel oil and gas discovery. Overlying it was a large gas hydrate accumulation. They basically went through a design criteria where they decided virtually to add two additional production facilities, move them off the crest of the structure to avoid the hydrates, what was in itself a billion-dollar decision. So again, this is a type thing what goes on every day in a company of evaluating risk associated with hydrates. This is one of the rare public projects where you can actually look how they've approached that. This is the same information, it's only on a timeline. Again, just read it. The circles indicate geoscience drilling projects, squares indicate production testing projects, Japan, US, Korea, India, China, and then the permafrost environment, the long-lived programs on the North Slope of Alaska, the Malik programs in Canada, and also the projects in China, particularly on the plateau, and also the return to the science programs. And some of the interesting things about the science programs of the ocean drilling program, a number of them have moved into observatories. These are actually observatories where you put in different sensor systems, pressure, temperature, acoustic systems, and they're wired into a permanent grid where they're actually monitoring these sites, from everything from earthquakes to the response of the hydrates to the systems themselves. So that's our toolbox. This is what we know. One of the critical things to think about, toolbox only starts in 1990. First drilling program is 1995. The first theoretical consideration that hydrates even existed in nature was only 1965. So you're still starting to think of something that's relatively new when you think of it as a science or engineering problem. Next, Gulf of Mexico. So when we look at the petroleum system, most of the components should be familiar to you. We have reservoir, that's the container in which the gas hydrates actually occur. You have gas source and migration. Those are normal conventional oil and gas issues. Where does the gas come from? How does it move? And what does the reservoir look like? We've already talked a little bit about reservoir and the fact that we're going to focus primarily today on sand reservoir. There are fracture-dominated hydrates, there's disseminated hydrates, and others that require very large technical increases in our knowledge to be able to assess or approach those resources. At the top of a gas hydrate resource or systems analysis is like gas hydrate stability field. I assume everyone knows that gas hydrates is under a limited range of pressure temperature conditions. You can map the zone in which hydrates occur, both in permafrost and marine environments. But so when you start out in May, I have a Van Tile lecture, so stay tuned, you can come to that. In May, we'll all talk about exploration approaches in systems. And we'll talk about how do you calculate hydrate stability fields, how do you evaluate the source and migration characteristics, and finally the reservoir. The rest of the day we're going to talk about reservoirs. So again, sand reservoirs. This is a return of our pyramid at a very different look. Ray Boswell and I came out with 2006. It shows there's value in very simple concepts. It basically put into context when we would walk into a manager's office in Houston saying, okay, Tim, I've seen this picture of a hydrate outcropping of the seafloor like this in the Gulf of Mexico. How do I produce that? Is that my resource? And we come back, no, your resource is at the top of the pyramid. It's in the sand reservoir. It looks like this from the Nankai Trough, made up of a quartz sand system. We actually have a conglomerate from the Malik site, where the hydrates is the actual white material. A lot of the white material in there is the actual gas hydrates themselves. So we have a solid form of natural gas and water, and a crystalline form that occupies the pore space within these porous mediums. Not occurring as disseminated types or as a resource issue or even these fracture-dominated hydrates. We have two assessments, what I've highlighted at the top of those, and this is what we kind of do for a living. At the Department of Interior, we did the only now completed technical recoverable assessment for gas hydrates, and it's on the North Slope of Alaska. I could go into that, and the reason we felt we could do that is because of the database we have with 3D seismic, that we could actually map prospects. We estimate on the North Slope of Alaska there's 85 trillion cubic feet of gas within the hydrate phase that's technically recoverable. Also related to this, within the BOEM assessment, within sand reservoirs, so the BOEM, it's a government agency that evaluates resources in the offshore environment. They've recently assessed the offshore portion of the Atlantic margin, but also the Gulf of Mexico, at over 15,800 trillion cubic feet of gas in place on the Atlantic margin. So you start putting that context, that number into context. That's within sand reservoirs, so that's important. We've moved away from just shales within the sand reservoirs in that one basinal setting. So again, that just gives you a context of scope and size. Again, the pyramid indicates difficulty in production and characterization. So let's stay to the top of the pyramid. Why sands? Sands basically gives you a pore in which to nucleate the gas hydrates. It gives you a way to migrate gas into a volume, into your host rock. It gives you the ability to actually nucleate the gas hydrates in that porous media. It also gives you the ability to perturb it. And what that means is, if I'm going to produce a gas hydrates, as we'll talk about shortly, I'm going to change its temperature or I'm going to change its pressure. To change its pressure, I'm going to want to put a pressure gradient into the formation. That porous medium, that's what we're going to talk most about, is there actually the presence of effective permeability within a hydrate reservoir which you can draw pressure down. So that allows us to basically do that. The other thing, we can look at multiple well completions in interrelationships, just like you do in conventional oil and gas, and looking at well interference between various wells. All of these things we have done in the model world. In models, no one's done this in the real world, and that's what we'll talk about here for the rest of the time. So the Gulf of Mexico, one of the best areas, one of the best developed studies looked at the prospecting of gas hydrates. Okay, by the time we reached the JIP, Leg 2 expedition in 2009, we were looking for hydrates in sand reservoirs. Before this time, we were looking for anomalous reflectors, what indicated the base of the hydrate stability field. This map shows the Gulf of Mexico in a prospecting phase, more or less. This is a bathymetry map. The modeled area where you see this roughness is the area of the salt tectonics within the Gulf of Mexico. You have a disturbed seafloor. It's disrupted by the density-driven drive of the tectonics of the salt systems themselves. But we also seen from our friends at BOEM, Bill Shedd and others, we've seen in their work, BOEM has access to all the seismic data that's ever been shot in the Gulf of Mexico. They actually have merged this at 50-meter bin spacing for the entire Gulf. So within their project, their ability to work in a daily event, to go through large areas of the Gulf of Mexico, mapping seismic evidence for the presence of gas hydrates. These are different indicators showing on this map. We don't really have that time to go into it today, but basically they're showing areas where hydrates have the potential from seismic evidence to occurring. We have two drilling projects, the 2005 project marked by X's, which focused mainly on fine-grained sediments, and then the leg 2 in 2009, which focused on coarse-grained sediment reservoirs. A very simple concept is that in this exploration mode, we were looking for where do sands occur in a marine environment, and what are the indications for that. We're basically going to look at a model where we're going to look at one of our drill sites. There's several others would have very similar occurrences of gas hydrates, but in different geologic environments. We have Walker Ridge 313, where we discovered hydrates in sand reservoirs. This is called a mini basin. It's a small topographical feature on the seafloor, which basically has a changing gradient. What's happening, sediment just doesn't get deposited off the slope. It actually gets channelized into different geologic environments. So this is the sediment water at the beach. Sediments and water are getting carried down different channelized systems all the way to 300 kilometers offshore into large fans, systems, and others. But internally, particularly in the salt mini basins, we have changes of topography that allow that energy, that high energy deposition environment to drop out the sand into reservoir environments. So this is a map of the seafloor of the Terrebonne Basin, it's called. We have what's a very good geologic setup, small inset, a small entry into the basin, very small outlet. This is a negative, or basically a basin within the surface itself. So as the high energy sand and water comes in, it basically sees a reversal in gradients and the sands get dropped out. So this is an ideal geologic setting for accommodation space for the occurrence of sand reservoirs. When you look at the seismic data from this area, and I agree this is time and seismic, so we're seeing bedding planes, but one of the things as a geophysicist you look at, you see these interesting reflectors which seem to be changing their phase. And what that means is they're changing their velocity. In this sense, the reflector above seems to mimic the seafloor. It's a high velocity event, and below it seems to be a low velocity event. So the first interpretation of this, that this was a zone of hydrates trapping down dip free gas accumulation along the base of the stability boundary. So let's take a little closer look. This is what's called a phase reversal. We actually have a switch in the amplitude of the acoustics, what's indicating high velocity to low velocity. We have the predetermination, pre-drill, is the occurrence of gas hydrates, gas below, trapped in those reservoir systems. And we drilled 2 wells at these sites, both the G well and the H well. We're going to focus on the geology of the orange horizon. So we're going to map this horizon. How are we going to do that? We're going to use amplitudes. So this is the acoustic energy, the reflection coming off that horizon, and amount of energy coming back to us, what gives us information on both the phase of that reflector, but also some information on potentially the content of that reservoir itself. In drilling, and this is the well I'm talking about, the H well, we drill the orange unit right there. What we found was a low gamma ray zone, thick sand section, about 50 meters thick. Sorry, this is long country, 50 foot thick. We have very high electrical resistivities. Hydrates are an electrical insulator, just like oil and gas. Believe it or not, you can use Archie relationships. You can use many configurations of normal well log evaluation techniques to characterize hydrates. As we march across, finally we see about 50 feet of gas hydrate bearing section with hydrate saturations as high as 80% within sand reservoirs. So our pre-prediction basically shows that we were accurate. This was and then you're actually able to map these horizons. In this geologic setting, again, in one of these maps, is that this is an amplitude map. And to again explain this is a map of that orange reservoir. You're basically taking the amplitudes of it. You've looked at both the phase and the intensity of that amplitude and looked at in different color bar scale. The purple is indicating the highest amplitudes. This is in the up dip position, and this would be within the hydrate stability field. and this part would be below the gas hydrate stability field. So if you remember from the map, we're basically mapping from above to below along that reflector, what's now flat. What we see is evidence that we see significant organization of the amplitude features itself. As a geoscientist, you go in and determine this looks like a levee deposits, what are very conducive to sands. You see a main channel, what's mainly clay fill, with a sum of a lag deposit in it. But the thickest hydrate occurrence here at the H well, what we just looked at, this is the same well, is the 50-foot occurrence of sand. So what we've done in this sense is that we forward predicted with the seismic data. We've gone through a systematic analysis of the amplitudes. We actually have inversion techniques to look at hydrate saturations and thicknesses. And then we step all the way through to finally to the drilling program, have confirmation of hydrate occurrences with a levee sand deposit, basically with these occurrences. And we've been able to repeat this throughout the world. Again, this was really one of the first projects where we had a fully developed ability to explore for gas hydrants and move forward. Okay, now I want to talk about production. How do you produce gas hydrants? So I got one phase diagram, I lied. So we have hydrate phase diagram. This is the geologist's view of the world. Pressure goes this way up, so sorry about that. And then temperature. And then what we have is anything within this field, of course, with the presence of gas and water together is in the form of gas hydrates. To produce a hydrate, you've got to change its pressure, change its temperature, or both. The other aspect is inhibitor. This is a simple concept. It's acting, if you look at old work in the Soviet Union and others, you actually see places where they injected methanol and salt into the reservoirs themselves and others as a chemical injector. So you're mainly moving the phase boundary in that type of setting. One concept that we'll touch just very little of is CO2 displacement. And this is the concept of actually the fit of the methane molecule within the gas hydrate cage structure. The CO2 molecule actually fits better. So the theory was, and then proven in a laboratory at ConocoPhillips, it was shown that if you actually could inject CO2 into a hydrate-bearing reservoir, it could potentially displace the methane and sequester the CO2 within the cage structure itself. We're going to talk a little bit about one of these projects, what was conducted on the North Slope called Ignat-Sakumi. So, pressure, temperature, chemical exchange, injection. When we look at our history of production testing, and this is what we're going to focus on for the next 5 or so minutes, we've had a very short history. But it's also been combined into two areas. When you look at something like gas hydrates, where we're at today, we've had about 150 years of oil and gas production. So how do you predict future production? Well, you look at the past. With gas hydrate production, since we've had no production, how do you predict the future? Basically, you rely on modeling. So the modeling programs, we have about 6 of them that are active in the world today. Some of the most advanced programs, the Tough model that actually came out of Lawrence Berkeley National Lab. We also have production models with our JOGMEC colleagues and a number of others. We also have production models in this room and others, so in the Petroleum Engineering Department. So when we look at gas hydrate as a production modeling issue, this diagram tried to capture both what we know from production modeling, but also what we know from our very limited amount of production testing. And this should be somewhat discouraging because it tells us how little we know still. At the top of this diagram are the very limited number of production tests. These production tests were all designed as simple experiments, very short duration, 5 to 10 days, up to 26 days is the longest one. And what they're all designed to is look at one single variable, such as heating the formation, or heat exchange of the formation, or relative permeability. They're not designed to look at commerciality of gas hydrants. So when we look at the production rates, we see production rates for onshore environments at the highest rates of only about 60,000 cubic feet of gas per day. Again, experiments not designed to look at deliverability or commerciality. We also look at offshore. The only production test that's been conducted is those at the Nankai Trough site in 2013, and they achieved rates of about 70,000 cubic standard feet of gas per day. That was only a 6-day test. So we'll come back to this repeatedly. But the production models, of course the model tells you best stories. So what we have is what are very reasonable. These models consider, we believe, all the phenomena of gas hydrants. All the phase exchanges, all the issue of heat exchange, the permeability, the porosity, all the other components of the reservoirs themselves. On the LPAD and the Malik sites in the Mackenzie Delta and the North Slope of Alaska, in the permafrost environments, we see predicted production rates around about 4 million standard cubic feet of gas per day. If that's set down here, somewhere in eastern Colorado or the Julesburg Basin or something like that, it would be a very nice production rate. But this is the North Slope of Alaska and others. When we look at the marine environment, we look at much more complex completions, including horizontals, fracturing reservoirs, other considerations. We've seen predicted production rates as high as 40 million standard cubic feet of gas per day. Some of these issues are also because these reservoirs are very warm relative to the hydrate reservoirs we see, so you can drive these much harder. Keep in mind, hydrate dissociation is an endothermic reaction. So if you're in a marine environment where these reservoirs at 25, 30 degrees Celsius, you can drive them very hard, and with the driving force being depressurization. These reservoirs in the marine and permafrost environment are at about 5 to 12 degrees Celsius. When you start driving them, the driving force being depressurization, you can't go as far before you get to critical point and start freezing fluids. So this tells you two things. It tells you basically that we have a great deal of range of uncertainty, and that the amount of production testing that's been done is insufficient to calibrate the production levels yet at this time. So what is our history as we look forward to production testing in the marine environment and look at the reservoirs now? In the Nankai Trough, we had the first production test of the 6-day test. We have an ongoing test which starts its flow period about 3 weeks from now, but it will only be a 2-month-long to 1-month-long test to look at the mechanical completion, to look at the completion, the sand control designs, and others. And we're looking at about a 90-day production test, even though that's not referred to, it's referred to as extended. Again, mainly looking at the mechanical completion, because the survivability of these wells as we move to multiple years is still uncertain for gas hydrates. When we go to Japan, where the production test was conducted, we have extensive information on the Nankai Trough and others, particularly the production test site was indicated by the star. We have previous geoscience drilling expeditions across the area of the Nankai. In the site, what's called the beta test site, we have a well log here. It's difficult to see, but this is the very bright amplitudes, again, associated with the hydrate occurrence. It's a channel levee system, very well mapped, very well characterized. It's been mapped to determine it has about 20 trillion cubic feet of gas in place within the sand reservoir component. In the immediate area of this well, in the surrounding area of the mapped accumulation, in this case, as high as 10 to 83. So again, we have a range that's characteristic of all assessments, but this is the individual map distribution of this single accumulation that we're talking about now. In the production test, it actually included a production test hole, observation wells, and others. We had 6 days of testing with cumulative of only about 120,000 cubic meters, with about 20,000 cubic meters of gas per day production rates. Not a terrible bad production rate, but again, not intended to actually demonstrate commerciality. That's our inner. For the permafrost environment, our database is a little richer. We reach back to some historical work on conventional gas fields in Russia. We move through some historical work in the Malik sites in the Mackenzie Delta. The first thermal depressurization tests were really designed to understand hydrates properties in 1982 and 2002. And then we finally see what we'll see is some production testing in the form of wireline formation testing in 2007. It's more reservoir characterization we'll talk about. Malik sites, again, a 6-day test is the longest we look at. And then finally, the ConocoPhillips site, what we'll take the last look at the last slides today. Looking at not so much the CO2 methane exchange, we'll look at the 25-day depressurization test at the end of the project. And finally, on the plans for our extended multi-year production test, what's being planned now for the North Slope. On the North Slope of Alaska, we've had 2 main projects. The 2007 BP project was a stratigraphic test well with limited pressure drawdown test, but very extensive coring and physical property analysis. And that's what we're going to finish off talking on most of it. We'll come back to the CO2 displacement test. I'm not going to talk really anything about the methane CO2 exchange. It's a very complex issue. It does not appear to be commercial with existing technology and understanding. I'll leave it at that. And it's a very complex discussion. Just with a 45-minute talk, it's hard to go into everything. But it's an important issue to consider, but it's poorly constrained. All of our considerations today are on depressurization. So the the Mount Elbert site in the Milne Point, just north of the Prudhoe Bay oil field, in a field called the Milne Point field, we have two 50-foot thick gas hydrate accumulations. These are thick, high-quality sand reservoirs, what we were able to seismically map beforehand and distinct structure core and actually recover the hydrates themselves in that setting. We also did open-hole MDT, modular dynamic tester. It's a wireline formation testing tool, work on that reservoir. We also have nuclear magnetic resonance logging. So you can see where I'm going to talk about the reservoir. In these sand reservoirs, this was the discovery. We had insight into this for the Malik program. It was only 5 years before this. We came to the Mount Elbert project, and we said, okay, we repeat the NMR logging. Nuclear magnetic resonance logging by this time was quite advanced. And what was very interesting to us, and I won't go too much through the display, but the critical issue was the discovery that before this project, before the Malik project, we thought there'd be almost no permeability, effective permeability in a hydrate reservoir. But we determined we had an effective permeability of around 0.1 to 10 millidarcy based on the NMR analysis within the hydrate-bearing sections. These were in hydrate-bearing sand reservoirs, about 80% saturation. What was even more interesting from the NMR analysis, we had a mobile water phase. We could actually pump on these reservoirs before dissociating hydrates, move water out of the reservoir. We could do it pretty freely. We could effectively pump on that reservoir continuously. So we were seeing a mobile water phase, and we were seeing evidence of relative or effective permeability in this presence. So that was a very important discovery at this time in our understanding. In the next part of that, we went through the analysis of an MDT test. So we did a drawdown MDT test where we had transient analysis and flow analysis. We came up with effective permeability of about 0.1 to 0.17 millidarcy. So when we start looking at these numbers, we start seeing a closing. And we generally are saying, okay, the permeability of these highly saturated sand reservoirs are around about 0.1 millidarcy for the effective permeability in these type of settings. So we were moving forward with that understanding of the system. So then we went back to the log data and looked at different models. So this was a critical part. We're saying there's a mobile water. How did the hydrates occur in the porous media? So again, we have porosity, we have hydrates, and we have free water, we have bound water, we have other phases. This is modeling work we did from acoustics, and this is out of work what mainly started at Stanford University, and what they were looking at was different acoustic models for the occurrence of gas hydrates. Hydrates filling porous media, hydrates occurring and supporting the matrix, part of the load-bearing system itself, coating the grains, hydrate growing on the grain surfaces itself, or hydrates actually at the grain contacts. And within this, we basically, very simple concept is taking the shear wave data from the well log, and this is the P wave data from this well log, and this one is also a VP-VS ratio. And each of these lines represent one of these conditions. For example, the blue line here indicates the cemented reservoir, basically where the hydrates in this type of acoustic model, for the occurrence of gas hydrates, velocity of hydrates is about 3.25 kilometers per second, so it's a solid. Its behavior is such, if it occupies this, any of the hydrate-bearing zones that are forming as a cement should fall along that line. The same for grain coating, supporting matrix, and pore filling. In both of these, and these were all onshore settings of permafrost environments, we see evidence that the hydrates appear not to be coating grain surface or pore filling, but being more part of the load-bearing system. They seem to be participating, but the most critical issue, they didn't seem to be actually coating the grains. This indicates we think these are water-wet systems, much like conventional, most oil and gas reservoirs. The hydrates occur in the bulk pore phase, but also part of the load-bearing component. If we link it back then to the permeability issues and others, this is the mobile water phase that we're able to move during the test. This is where our effective permeability exists. This is where the free water exists. These are all really good news if you're thinking about producing gas hydrates. Along came pressure coring. So does things change? With pressure coring, we start looking at the ability to recover the cores at in situ condition, bring them to the surface, and do analysis of these cores that have never been depressurized. We're able to look at everything from effective permeability all the way through components of acoustic properties, shear wave properties, all the mechanical properties of these rocks and others. So very advanced technologies are ability to do that. We have several labs in the world, particularly AIST in Japan is one of the leading groups in the world that we work closely with in many of our partnerships. What came along in some recent publications out of Japan was that we had our world of gas hydrate saturation and MDT NMR, kind of 1 to 0.1 millidarcy. We were happy. Alaska was telling us everything we needed to know, that we thought we understood where the permeability reservoirs are. The pressure coring from the Nankai trough started to indicate higher effective permeabilities. So this becomes an issue because every order magnitude increase in effective permeabilities is order of magnitude increase in production rate. So this starts becoming a pretty important variable to get a good handle on. This turns out to be the same thing we started to see also offshore India. I'll show you one of these plots. So the concern became, oh, this is a marine environment. Maybe there's something different than that in a permafrost environment. So we went through the same analysis, our Japanese colleagues, and they showed again, the hydrates in the Nankai Trough are part of the load-bearing system. They're part of the frame. So both settings, at this level of analysis, we're saying that the hydrates appear to be part of the frame system, both the marine and permafrost setting. But we have this now new data set from pressure cores. Well, there could be an error. We certainly agree with that. And others, but we're seeing a distinct different range of permeability data for those. Again, as I mentioned already, in India, this is a bit hard to see. These are two pressure cores, 1.2 meter length. These are high resistivity zones, or the actual occurrence of gas hydrates. What I wanted to note in here in these two boxes, this is showing a 76% saturated hydrate with 74 millidarcy permeability, and this is a hydrate saturation at about 66% with 15 millidarcy. I wouldn't worry a lot about the absolute values. There's other effects on some of these issues, but what I basically wanted to show here again was this uncertainty, what we really need to think about, because our biggest focus now, and if I show a production diagram, we now bracket all of our production models between 1 and 10 millidarcy for our different production models with effective permeability, and that alone has dramatic effects when we look at everything from the economic analysis to just the tubular designs and the designs of our test wells. So this is a big unknown, and we don't really, and I can sit, we can speculate and talk more in the discussion part about where that comes from. The last thing I want to talk about is a little bit from Ignik Sakumi, and again, a CO2 methane exchange project. Very simply put, this is a well, this is called the Ignik Sakumi well. This is a resistivity bearing zone. We perforate a 30-foot thick section, high electrical resistivities, high hydrate content. The zone is perforated, you set screens, you inject a mixture of CO2 and nitrogen. If anybody wants to study nitrogen, it's the problem in analysis. And then you flow back. I want to talk about the flow back. When we look at the flow back, this part of the test, and how you want to read this diagram, this is the hydrate stability curve for pure methane hydrates. This is the pressure curve shown here in the green curve. So when the green curve comes along and drops below that boundary is when the in situ methane hydrates melt or dissociate, because you drop below the pressure temperature field for the hydrate occurrences. What we also see on this diagram is gas production. This is gas production, and we have cumulative production. So this is rate, this is cumulative production, the methane hydrate phase boundary. All the CO2 world's over here, and you can tell it takes you a little time to work through that, and it takes me about a half day to get through it myself. So, but we're going to talk about just that last part, production phase 2. So all of this deals with CO2 methane exchange. This deals with depressurization. We're going to look at the point where the pressure of the well, the wellhead pressure, is dropped below hydrate equilibrium. So how to read this diagram is the top of the curve. The red line is the pressure, is the wellhead pressure. So as we move down, each one of these is a drop in pressure. This is 800 to 300 PSI. Okay, this is the range. So we're only at a depth. Initial depth is about 2,600 feet. So hydrostatic is we're about half of hydrostatic. This is the actual production. And what's interesting to us is the next component is temperature. So we have a fiber optic that's behind the borehole out in the casing. So it's measuring the temperature of the formation. So this is the top of the formation. This is the bottom formation, and this is time. So everything's on the same axis. So if we come along, we basically lower the pressure of the reservoir, drops below hydrate equilibrium, we get gas production, and what we see is the well to begin to cool. The formation is cooling because hydrate dissociation is an endothermic reaction. What's important about this gives us the insight to what that multi-year test is likely to look like. Because what happens, we see the well cooled, more or less equilibrate, at a constant production rate almost, slightly increasing. Then we drop the pressure again, only about 10 psi, we see the production rate go up, we see the temperature cool. This well, after only a couple days, after 5 days, was already tuned. What I mean by that, every time we drop the pressure, the driving force, the production rate would go up and the temperature would go down. And as you watch each one of these breaks, you can basically see they line up with the fiber optic temperature change. And I'll argue to you this is, even though this well is kind of buggered up with all the CO2 work and others, I don't think you can take any of the absolute values from this well, but it shows you the direction. It shows you basically a well, and the heat is coming from where? Everywhere else, everything around it. So you're basically, the production rates is going to be controlled by the heat replacement due to the hydrate dissociation. So that heat replacement rate is actually going to control your production rate. So each one of these are going to get more or less tuned within a working range. And that's our critical thing. What we have to really understand is use this data to calibrate our production models, but understand this balance between pressure, temperature, and production rate, and basically look at that relationship. So relatively straightforward with a lot of details around the edge. So summary, we're basically targeting worldwide about 40,000 trillion cubic feet globally. We're looking at about 10,000 domestically in the U.S. from the BOEM assessment of in place. The first assessment's on North Slope of technical recovery of around 85 trillion cubic feet. Come back in May and we'll talk about exploration technology and characterization technology. It's quite advanced now. It's definitely major room for improvement, but we're moving quite quickly. The main area right now is looking at production technology. And when we look at production and production responses, we see right now predictions as high as 40 million standard cubic feet of gas per day from relatively complex completions. We see very high recovery rates, and we can explain that. It's a very simple engineering displacement issue. You almost have to from the hydrates because of the large volumetric exchange to get high recovery rates. Long-term tests are required. Alaska is a place where we're trying to set up a pilot right now in the BP unit for 3-year tests to actually look at, stay there and look at depressurization technology. It will be challenging. In our cold reservoir, low pressure, production water subsidence concerns, and environmental concerns. And this is what I spend most of my time on now. Look at the mechanical response to the hydrates and others. So I went a little longer than I had hoped, but thank you very much for your time today. And I have no place to go other than home, so what I do like, but questions or anything?
So the 40,000, this is like modeled or tested
Modeled.
for a vertical well, horizontal well?
The higher production rates are mostly horizontal wells with very advanced kickoff techniques. But most of these, and it's always the issue, to increase production rate is mainly a surface area phenomenon. You have to expose more hydrates to production because you increase the surface area of production. So right now, we don't worry, those are, other groups like to do those. For us, we're working on still first principles. We're doing vertical well testing, constraint between 2 shale beds, and we're looking at a closed chamber more or less test because we're using that data to calibrate the production models.
Any fracturing test?
We haven't done that. There's studies, particularly groups out of Singapore, would have some of the most extensive modeled studies against to look at fracturing of hydrates. It appears to be favorable, but again, we've done only 2 flowback tests trying to fracture hydrate reservoirs at MDT scale. They do behave plastically, so they do deform, to that, but none of them have been constrained in the test. The work from Singapore says that you can fracture and that in these reservoirs that you could actually maintain permeability into the reservoir itself, but they're very unconsolidated. These are shallow reservoir systems, both in marine and permafrost environments. The other thing is, when someone does finally talk about the commerciality, it's much like shale gas. It won't be someone drilling a vertical well. It's gonna be someone figure out a way to increase that surface area. One of the things we look at now is everything from methanol injection to create surface areas, you know, at the kickoff. Also even concepts of injecting nitrogen gas, which dissociates hydrates very effectively as a partial pressure phenomenon, create pathways where you would not have a permeability issue or a phase issue of fluids. So there is commerciality concepts, but right now we're back still just trying to figure out, I put energy in, what do I get out? Yes, sir.
You have two questions. One of them is, are there any commercial production at all?
No, sir.
Number two, I think you had a really important issue, alluded to it, the environmental issues in regard to
Right.
what is being emitted at this moment into the atmosphere. Do you know what the numbers, estimations of the numbers?
For the natural systems right now, just 2 weeks ago, Carolyn Ruth with USGS, was one of my closest colleagues, who does mainly the environmental aspect of our program and others, suggests that basically, and this is my own research too, that hydrates are not likely contributing significantly to modern carbon cycling issues. The reason for that is that the hydrate systems are extraordinarily well buffered. For example, on the North Slope of Alaska, if you warm the surface today to a temperature 10, 12 degrees Celsius warmer, what's the temperature of the ocean? The hydrates, when you see that for 10,000 years. So it's a lead lag type thing. In the deep marine environments, below about 5,000 meters, the ocean waters are very old. They haven't turned over. So there's a little thermal effect in deep systems. The place where there's a concern is on the continental shelves, that have been flooded over the last 110 to 120,000 years. So in those areas, they're more towards, you know, that buffering has gone away. They're more on the edge. But in that environment still, the volume, what's been predicted contributing, has been estimated to be very small. No one knows, but when we look at the climate change issue, is a time frame. We think on a human time frame, a 100+ year time frame, there's likely not an issue, likely. And that's a very key word because research is required. On a 10,000 time year, you know, kind of the interglacial 110 to 100,000 year, there is no evidence that it's played a significant role in any of the glacial events. It appears to lag all the major thermal events on the globe. The next, or sea level changes. The next one is longer periods of 1 million years, like the Pale-Eocene thermal maximum is about 1.5 million years long. It appears that hydrates played a role. And that was a long enough time for the whole sink, you know, that source to move to another part of the carbon cycle. And that's the critical thing. When you think of climate change, you think of aspects of these resources, or just the role of carbon, understanding the lead lag times, where all the sinks and sources are, and how they interact.
Well, that's great news, but one other thing too, as you well know, the hydrate center here,
Right.
they look at gas hydrate formation within pipelines and things
Sure.
like that, which is a flow assurance issue. But does USGS also get itself involved in that regard?
We do, in the sense that we have had long the history of working with Carolyn Coe's program and Denny's before that, and others, and we don't look at flow assurance issues itself, but what we do is look at a lot of the basic thermodynamics and kinetics, what comes from that science. That's almost like that three-legged stool, and one of my hazards is flow assurance, because what we find is hydrates, you can't give up any piece of data or any piece of theory, and it's always the predictive aspect of knowing where something's going out of science, what's this new. And this is a remarkable field. We contribute day one as a researcher. I mean, there's so little still known. Yeah.
The resource calculation.
That way. So, yes, sir. Yes, sir. Go ahead. Be my guest.
For the resources, 40,000 PCF, how comfortable this number come up? This,
Comfortable.
and let's say we have like we call reserve, right?
You know, I'm real comfortable if you don't hold me down to how many molecules and where they're at. But to myself right now, I have never done a global assessment, and I at most I've done national scale assessments one time. Now I'm down to basins, and that leaves me a little nervous, and I get nervous at a well scale now, so my point is, it's a very large number, and I think as a geoscientist, if I'm worried of a global climate issue and others, I don't think I'm worried about the volume. I'm gonna look more at the chemical record of the Earth stored in cores and carbon record to understand what contributed to the carbon, composition of the Earth's atmosphere. Try to do this pool estimate of how much something there is through geologic time is difficult. I'd rather look at a record of where the record has recorded those changes. What I look at as a resource issue it's a big number. Now I throw that away, and now I come down, okay, what are the next issues? What are the geologic controls? Can I map their accumulations like we can in the Gulf? I mean, we had close colleagues, Shell and others said, oh, there's no shallow sand reservoirs and hydrates now, in the Gulf of Mexico. And we're very effective when you go to collect the data at the scale that's necessary. So I'm very comfortable at some of the numbers when we talk about like the 10,000 trillion cubic feet in sand reservoirs within the U.S. and the offshore and Atlantic Pacific margin. But again, that's an in-place number. It's not anything about how it's distributed, how it's interconnected and others. So it's a big number than I worry now. Most of our driving force now, I don't think we should spend much more time improving upon the numbers until we understand if it's producible. That's the justification. As a scientist, but I can spend a lot of time just on the numbers. So.
You were showing a chart where you had pressure drawdown with
Yeah.
temperature cooling.
Yes.
So, do you have an assessment of what the region is that is being affected by? Where are you producing from? How far out is the sun go? Because that's really interesting. It's a 10 psi kind of difference.
Right.
It's
And
a
these
10
are all.
PSI difference.
Yeah.
And you have sustained production, so it means that
Right.
perturbing the right area.
And you're starting to reach, and we
Yes.
know,
Yeah.
like in the Japanese test, they reached 30 meters of a pressure effect. 30 meters in 2 days. So that permeable phase. So when you start thinking about, and that the thermal transit actually made it all the way to the well too in 6 days. And that's still, I don't quite understand it, because it was a negative thermal contrast. You think of endothermic cooling, but it's occurring way back here. I would actually think that you would be expecting warm fluids moving through from outside. So I've always had a little problem with this. So that's between all of us experts. But the main point is the reservoirs seem responsive. But thermally is just a no-win game, because as we know, trying to put in the original Malik program 2002, we knew going in, we tried to heat the reservoir, we put 90 degrees Celsius as a conductive heat flow problem of heat to the formation through circulation, and we dissociated 2 centimeters of hydrate over a 2-week period. But when we look at depressurization, both in the models and others, you see radiuses, but the radiuses are still relatively small. I mean, even after a period of seeing production rates over 1 million standard cubic feet a day over a year, you're still only reaching about 30 meters, because you have that large volumetric capacity.
So when you look at 10 psi pressure difference and that amount of gas associated, you still don't lose the production, which means there is no slumping, there is no compaction.
As long as you're, well, there is. And this is where we start, this is where I spend most of it. So the big thing, you gotta keep everything in the reservoir. It's the same control and all these issues. Most of the projects have done a very bad job at that. And that's just design. That's not something about hydrates. The other thing what we're most worried about now is the compaction of the reservoir once you remove hydrates. And what will be the permeability of that? Because we always just assume these are Darcy rods, on their own as intrinsic. But when you remove the hydrates, when I participate in the frame, how much compaction and loss of permeability do we see in that interface? And that's one of the things from AIST for the India course. First time we're getting evidence that we see significant drops in relative perms, but the problem is there's only been like 3 or 4 measurements so far. And they've been on, not ideal. Some of them have been more partially saturated or clay rich. So right now, that's one of our biggest issues of looking at is the consolidation state in the annular space after hydrate matter of where they're at in the system. So we focus on hydrates at phase boundary, so not deep. But the other thing is naturally, in many of these settings, in India, what are some of the best reservoirs we've ever seen, they just didn't have enough time. And also in the Gulf of Mexico, they're in some very deep water settings. These are some of the deepest wells ever drilled in the Christian River Basin, some of the deepest wells drilled in the Gulf of Mexico. And that then gives you a hydrate that's up to 2,000 to 3,000 feet below the seafloor. So then you start getting sediments that are a little more competent, and they have a characteristic that's a little more responsive, but has the hydrates been there since they first got deposited. So you start dealing with a lot of issues how the reservoir's going to respond. So the whole issue of compaction, particularly after hydrate dissociation, not so much at the sea surface, maybe at the completion, but I'm worried at the pore scale. That's where I spend most of my time thinking about the problem. Yes, sir.
So Tim, my question is, of these gas hydrate in the